There we go. All right, so today I want to talk about electron configurations. In yesterday's lesson, we talked about the fact that there is a nucleus with protons and neutrons. And then we talked about how Bohr discovered that there are energy levels. And electrons exist only in specific energy levels, all the way out to 7 energy levels.
At this time, would all freshmen, sophomores, and juniors with the last names starting with the letters H, I, J, and K please report to the auxiliary gym for school pictures.
Okay, so energy level 1, energy level 2, energy level 3, all the way out to energy level 7. There are 7 possible energy levels that have been discovered so far. Once Bohr discovered this, chemists wanted to know more. They wanted to know what is happening inside those energy levels. Are the electrons just flying randomly in those energy levels? Do they exist in specific places? And they did that, and they found out that it's actually more specific than just energy levels. There are things inside energy levels. So the biggest part of an energy level, or the biggest part, is the energy level. And it goes from 1 to 7. The number of electrons that can fit inside of an energy level is equal to 2n squared, where n is the number of the energy level. So the first energy level holds 2, because 1 squared times 2 is 2. The second one holds 8. The third one holds 18. Not going to fill in all of them, but. And then it just goes out.
Is this like the P1?
We're getting there. Okay, so 1 to 7 are our energy levels, and then inside energy levels, we have sub-levels. Energy level 1 has an S sublevel. Energy level 2 has an S and a P. Energy level 3 has an S, a P, and a D. And then 4 to 7 all have S, P, D, and F. Now, technically, we have not discovered a 6F or a 7F or even a 7D. There's nothing that's been found that's that big. But theoretically, we could someday, I guess. Then sublevels contain orbitals. The S is 1 orbital. The P is 3 orbitals. The D is 5 orbitals. And the F is 7 orbitals. And then that's where you'll find the electrons, is inside the orbital. And there are 2 electrons per orbital. As long as they have opposite spin. Remember that? They can't be in an orbital together because they're repulsive. So the only way to make it to where they hypothesize that they're spinning in opposite directions, clockwise and counterclockwise. Okay, so electrons. There are energy levels. Energy level 1, 2, 3, 4, 5, 6, 7. Then those energy levels contain sublevels. The first one has an S sublevel. The second one has an S and a P. The third one has an S, a P, and a D sublevel. And then all of these out here have S, P, D, and F. The electrons in the energy levels have to then be inside of a sublevel. So here we would have a 1s1 electron, 1 being for the first energy level, S for the S sublevel, and then 1, superscript 1, meaning it's the first S electron. And then there's a 1s2 electron, the second S electron. Then there's a 2s1 and a 2s2. There's a 2p1, a 2p2, a 2p3, a 2p4, a 2p5, a 2p6, because each one holds 2. And then 3s1, 3s2, 3p1, 3p2. You remember this? Yep. So if we draw these orbitals, the S is one single line for one single orbital. Because if you remember, the S is spherical shaped, and we only have one orientation of a sphere. You can't change a sphere and make it look any different. In a three-dimensional space, a sphere is a sphere. The P has 3 orientations, 3 orbitals, because it's this infinity sign, dumbbell shape. And it has 3 orientations in a three-dimensional space, X, Y, and Z. The 3 dimensions, X, Y, Z. So we have PX, PY, PZ. The D is too complicated to draw, but it has 5 orientations in a space. They're like XY, XZ, YZ, X-Y, things that I don't really know, but there are 5 of them. And then F is 7 of them that I couldn't even begin to describe. And each of these lines represents a home that will hold 2 electrons as long as they're spinning in opposite directions. Clockwise, counterclockwise. Okay, so then this drawing is complicated and doesn't really represent what's going on. So chemists kind of flattened it and made it into an orbital diagram where we have the nucleus down here and we draw in these orbitals. So 1s is my energy level closest to the nucleus, my orbital closest to the nucleus. And then 2s, and then 2p. S is a little bit closer to the nucleus than p. They're still both in the second energy level. This is all one energy level, but S is just slightly closer than p. These are the 3 orientations, X, Y, and Z. That's it. The second energy level only has an S and a P, so we move on to 3s, then 3p, then 3d. That's the third energy level. But then this is where it gets tricky, because the fourth energy level, its s orbital, s sublevel, extends down below the 3d. So actually 4s is closer to the nucleus and gets filled before the 3d. Because it's an overlap. And the only way we know this is by experimenting on atoms and seeing which electrons get taken away. And remember, we always fill in electrons from bottom to top. And when we get to these, one electron in each before you start to double up. This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So this is neon. Then if I wanted to write this as an electron configuration, I would write 1s, and there are 2 of them. Then 2s, and there are 2 of them. And then 2p, and there are 6 of them. And this is neon. Okay, so this is an electron configuration. There are a million ways that you can go about figuring out the electron configuration. You could draw an orbital diagram. You could draw a whole big picture. Or you can use the periodic table as a map, and that's the easiest way. So that's what we're going to do. Let me pull up a periodic table. Okay, so if we look at the periodic table, it's organized into blocks. We have the S block. We have the P block. We have the D block. And we have the F block. The S block is 2 elements wide because 2 electrons fit in an S sublevel. So this is 1s1. This one, helium, is over here, but this is 1s2. This is 2s1. This is 2s2. Then we come over here. This is 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. And then we come back down here. This is 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. We come here, 4s1, 4s2, and then it gets a little tricky. This is 3d1 to 10. And then we're still 4p, 1, 2, 3, 4, 5, 6. 5s, 1, 2. 4d. This is 5d, 6. 6d. F is 4f, 1 to 14. And 5f, 1 to 14. You can use this to help you write electron configurations. So if I wanted to write the electron configuration for sodium, I would tell everything I have to cross to get there. So I have to go across 1s2. I have to go across 2s2. I have to go across all of the 2p6s. And then sodium is 3s1. If I wanted to do arsenic, I would tell everything I have to cross to get there. So I have to cross 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, and there are 10 of them, and then 4p, 1, 2, 3. That's arsenic. It's the third element in the P block of the fourth row. So it ends in 4p3. You can also do a shorthand version where you put the noble gas above, in the row above, in brackets. So argon is the noble gas in the row above. And then just do everything after argon. So argon, 4s2, 3d10, 4p3. On the AP test, unless they say the full electron configuration, you are allowed to do the shorthand one, the shorter one. But if they put full, you have to put full or you don't get credit. So make sure you read carefully. They will have, they almost always have you do at least one electron configuration. I've never seen them have one with an F in it, but they often have D's. A lot of times they give you ions. So say I gave you this one. Sodium plus, the electron for sodium plus, or the electron configuration for sodium plus. What does that plus tell me about sodium? It has lost an electron because it's 1 plus now. It's got one more proton than electrons. So if sodium loses an electron, now it has 10 electrons, and it's the same as neon. So 1s2, 2s2, 2p6 is the electron configuration for sodium plus. Most of the time, if you're writing an electron configuration for an ion, you're writing the electron configuration for a noble gas. Because atoms gain and lose electrons and form atoms to fill their octet and to be like the noble gases. The only exception would be if you're looking at gaining and losing from the D block, and we'll do an example of that next time.